So we're going to look at this example. Start this down here. And this is the idea of a multivariable rate function. And I'm displaying it as a contour plot, right? We said one of the four representations of multivariable functions was a contour plot. And so that's how I'm showing that here. And what this shows is this rate function is showing the rate of change of megapounds or million pounds of snow, fall in with respect to time and elevation. So far our rates of change have been like partial derivatives, where it was the rate of change of the quantity with respect to one variable or with respect to one direction in the xy plane. That was directional derivative. This is a different animal. So this is the rate of change of, in this case, weight. So W is going to be the weight of the snow in megapounds. And then T is going to be our time in hours, and E is going to be our elevation in 1,000 feet. So this rate of change looks like this. It's the rate of change of weight with respect to time and elevation. So it's a rate of change that has built in both changes, and so then the units of that are what? Megapounds per hour and 1,000 feet. Okay, so does that make sense? So what's the difference now? We have two multivariable, both independent variables are part of the rate. And so that's what makes it a multivariable rate function. Okay, so to have a multivariable rate function like that, you've got to have your quantities in the numerator, right, per your independent units, and then all of them, or in this case 2, will be in the denominator like that. Okay, so let's just interpret, just do a couple of practice here. Using the contour plot, interpret the situation for an elevation of 3,500 feet, and 1.4 hours. So here's 1.4 hours, 3,500 feet. So we get this point right here, and to get the value of the function, you look at the contour lines, and so this is 0.2, and this is 0.6, so this one is 0.4. So for part A, so this is, and we'll call the rate function W equals F of T and E. Okay? So we get the quantity W weight from the function F, and we know that function F is the rate function. That's right. So in part A, we are doing F of 1.4 and 3.5. And we get a value of what? 0.4, and that's going to be megapounds, like we said, per hour per 1,000 feet. Does that make sense? Any questions on that?
Yes, so what you're doing is you're just looking at it's similar to how you would look at various two functions of one variable, right? So you're just looking at the time per hours and then the elevation, and then you can see the rate of change for the weight of the snow in pounds. So,
yeah, so it's the same kind of contour plot that we had before, where if you stay on a contour line, you have a you're staying at a constant value of the output variable, in this case weight. But just now those values are rates of change instead of like quantity. right? So it's the rate of change per both independent variables. So B 1.8, same thing, 1.8, 5,000 would be what? 1.8, 5,000 would be about what? About 1 point, close to 1.4, again, megapounds per hour per 1,000 feet. Okay, so that's just reading the contour plot, right? We're just reading the contour plot like we did before, but now the output variable is a rate of change rather than just a like accumulated quantity.
Excuse me, Professor.
Yeah, sure.
Would your dot be shifted to the right for 1.8?
1.8 is here, right? Or here, sorry. Yeah, I got the wrong point. Thank you. Yeah, 1.8 is here, right? And 5 is here. So it should have been this one. And then this is different. So what should it be?
Is it 1.6 megapounds per hour per 10 to the 3 feet?
Right. Good. Thank you for pointing that out.
Okay, I just want to make sure.
Yeah, no, you're right. I had the wrong x coordinate or wrong t coordinate. Okay. So that's just reading it. So now how do we use this? We use it the same way, right? This is a rate of change. So rate of change can help us find what changes in the dependent variable. In this case, changes in weight. What do we need to calculate a change in weight with our rate of change?
In this case, time and elevation, right?
So what we're gonna need now is a combined change of both time and elevation. And with a change in time and a change in elevation, we can use the rate of change to find the corresponding change in snow weight for that time frame and elevation change. So we're about to apply the same thing we learned before, but now with this multivariable rate function. Okay, so now, all right, again, the W is weight, and that's equal to F of T. Oops. F of T comma E. So now we want to estimate the average rate of change of snow fallen between 1.4 and 1.8 hours and 5,000 to 6,000 feet of elevation. So looking at 1.4 to 1.8 and 5 to 6. So this is like a combined time range and elevation range. So it's like looking at this box on the graph. Okay, and so
Professor?
Yeah.
I'm sorry. Could you go over that one more time, please?
So we're talking about a time range. So this is like a dt from 1.4 to 1.8. So that dt would equal 0.4. And simultaneously an elevation change from 5 to 6. So then dE would be 1, changing from 5 to 6. So that would be focusing on this part of this graph, right? So time changing from 1.4 to 1.8, while simultaneously elevation changing from 5 to 6,000 feet. So we'd be looking at that part of the graph. Does that make sense?
Makes perfect sense.
Okay,
Thank
awesome.
you very much.
Yeah, sure. Okay, so we want to do something here. We're not going to estimate the average. We're going to look at this and say, we're going to pick a corner. We can pick any corner we want. And so let's pick lower left. Okay, so lower left corner is this corner right here. And we're going to assume a constant rate of change for the whole region here, for this whole change in T and change in E, equal to the rate at the lower left. So what is that rate at the lower left? Here's 0.6, here's 0.8. It's pretty much like 1, right? Or maybe a little bit more. So let's have this is 1.2. right? So maybe 1.05 or something like that, or let's say 1.1, okay? Somewhere between 1 and 1.2 is 1.1. So using the lower left corner, the rate of change at the lower left corner would be the rate of 1.4 comma 5 is approximately 1.1. And we're going to use that for the whole region as a constant rate. So I'm going to take that 1.1. I'm going to assume that it's 1.1 for this whole region right here. And now I want to know what is my resulting we want to estimate the weight of snow that fell during this time and in this elevation range. Now we're doing number 2. So that's like a dW. It's like a change. It's like a amount of our weight corresponding to what? T going from 1.4 to 1.8 and E going from 5 to 6. So how would I do that? How do I get the change in weight, the change if I have this constant rate 1.1 right here? What would my calculation be?
Would it be the area of the square times dW?
It would, but let's think about it in terms of the quantities rather than area at this point. So so we have a change in T of 0.4, and we have a change in elevation of 1. And so what is the rate of change? Given the change in your independent, the rate is the multiplier to get you the corresponding change in the dependent. So it's the same thing, rate times change in independent. So our rate is the 1.1, megapounds per hour per 1,000 feet. And what we're going to do at the rate of change by multiplying it by, what's the change in T? 0.4 hours. But now here, this is the multivariable rate function. So we don't do 2 separate calculations and add like we did with partial derivatives. This rate requires that we multiply by both changes, right? Because we have per hour per 1,000 feet. So we're going to multiply also by 1 times 10 cubed feet. But that's the unit, right? Okay, so it's the same concept as before, but now we have this multivariable rate function, which requires we multiply by both changes.
Professor Mark, can you repeat yourself? You're cutting out pretty bad.
Oh, okay, sorry. So this is the same concept that we've worked on with partial derivatives. We're given a change in your independent variable. Your change in your dependent variable is what the product of the rate and your change. So it's the same thing as that, but now the rate function is with respect to 2 variables, so you need to multiply by both changes. Did that come through better?
Yes.
Yeah, that was good.
Awesome. So then the hours are going to go away, and then the 1,000 feet are going to go away, and we're going to be left with megapounds, right? So it's going to be, what is this? 1.1 times 0.4. Is that 0.44?
It's 1.1 times 0.4. That's 0.44 times 1,000. So that's 440.
Well, but this is per 1,000. Right, so this is already per 1,000. So these units match up. So we're just times 1.
Okay, so then it'd just be 0.44.
0.44 megapounds. So a change in the weight of sand is like a little amount of the quantity, and that's what you get when you multiply place for this, sorry. That's good. Okay. So that's what you get when you multiply the rate times your 2 changes in independent. You get a little change in the dependent, which is a little amount. So based on compared to this whole mountain range, right? Compared to this whole mountain range, it's just a little amount of the snow that fell, right, in this time frame and in this elevation range. Okay, does that make sense? And again, it just goes back to dz equals, partial x dx. It's the same thing. But now your rate of change is in terms of two variables, so you need to multiply by both changes. And you still get then your change in the dependent.
So why did we use the lower left as compared to the lower right
We-
or the upper left?
Just because you can use any of them, and I picked that one.
Okay,
Yeah.
so
Right. That's a good question. So we can use the lower left, we can use the upper left, we could use the upper right, we could use the lower right. So I picked lower left. So now what about this estimation? Too high, too low, about right? What do you think?
Pretty close because we were right in the middle, right between.
Yeah, but I used this rate to be the constant rate for this whole square. So I'm assuming this 1.1 is the rate for this whole thing here. Look at what's the rate up here. The rate up here is 2. The rate here is 1.8. The rate here is 1.6. So is this an overestimate or an underestimate? A gross underestimate, right? This is a bad underestimate, very bad, because I picked off this lowest rate of the whole thing to be the constant rate for the whole thing, when really, as you move through this time and elevation, you have much higher rates, twice as high, right? 2, when you get to this up here. Okay, so this is a bad underestimate based on the rate being there. Does that make sense to everybody?
So what if you just took like the average of the lowest and the highest combined?
Okay, so that would be better, right? So another technique would be to kind of eyeball and say what one rate is better representative of what's going on here. So what would be better? Something in the middle, right? Something between 1.1 and 2, or 1.2, it's like some around 1.6, right? So if you picked 1.6, that would be, a better estimate, and maybe kind of close. But everyone would pick a different, right? Everyone would kind of come up with a different like eyeball estimate. The thing about lower left, and upper right, all that is that we'd all kind of do the same thing, right? So we'd get our rate there, especially if we had the formula for the rate, right? If we had the formula for the multivariable function, we'd all have the exact same rate, and we do the same calculation, and we get the same estimate. So how can we make this? I still want to use lower left corners, but I want to get a better estimate for this time range and this elevation. How can I do it? Oh, we're not quite there yet. So I just want to get a better estimate. Just a better estimate.
Take the lower left corner and the upper right corner and average them.
Yeah, so that's kind of what we were talking about before, like get something that's better estimate of the whole thing. But if I want to stick to the lower left corner, but I want to get a better estimate, what would that require?
This is a little bit like a Riemann sum.
Yeah, and what do we do with those? What do we do? It is a Riemann sum.
Yeah, it's like splitting up your rectangles or something.
Yeah, so we're gonna let's split it up. So if I split this up into 4, and again, there's no rhyme or reason. I could split it up into 16. I could partition this in many different ways. So I'm just choosing to, let's just split it in half both ways. And now let's use the lower left just for this part here. And then in this one, we use the lower left. So I'm going to do it 4 times. So for this little subregion, I'm going to use that rate. For this subregion, that rate. For this subregion, that rate. For this subregion, that rate. And you see this will be a better estimate because now it's kind of taking into account some of the fact that the rate increases from this point. And we'll get we'll see a higher rate. Okay? So I think this is question number 3.
So the more square, like the more sections you make, the more accurate the.
That's
estimate
right. That's right. So here's number 3. we partition the region into 4 equally sized rectangles. And now we're going to estimate the same total weight again, but with separate, so we're going to do separate calculations for each subregion, and then what will we do with each one? Let's make this 1, 2, 3, and 4. So this will be 1, 2, 3, and 4. So for subregion number 1, what's our rate about? It's this line right here, right? What is that? 1.2. So we'll do 1.2. Now what's my dt and my de? My dt is? For the subregion, it's half as what it was before because I cut everything in half. Same for that, so 0.2 and 0.5. That would be for subregion number 1. And then I'm going to take for subregion number 2, what rate do I have? That looks like 1.6. Again, my dt is now 0.2. My de is 0.5. So each one of these is calculating a little bit of snowfall for a little time change and a little elevation change. And we're using the lower left corners to do that. Number 3, that was our 1.1 times 0.2 and 0.5. And finally, subregion number 4, that is 1.4 times 0.2. Everyone see what I did? So it's the same, we're trying to do the same calculation down here, but with splitting up the region into 4 subregions and getting the little change in weight for each subregion and adding them together. Is this going to be higher or lower than 0.44?
Higher.
Certainly higher, right? Is it going to be, so it's going to be a better estimate because it's going to be higher. Anybody have this by any chance? Let's see. This is 0.01. Let me do this in our head. 1.2, 2.8, 3.9, 5.3, 0.53. So what's the unit on this? Megapounds per time per elevation? What does this calculate? What kind of thing does this calculate? A rate?
Would it just be megapounds?
Just megapounds. Just the megapounds, right? This is a second estimate for this amount of snow, the weight of snow that fell in this time range and this elevation range. And we expected it to be higher, and it was. Now what about this? Is this an overestimate or an underestimate? I think, were you answering? You were quiet.
An underestimate.
Still an underestimate, because in each subregion we have the same thing we had before. The lowest rate is in the lower left corner, so you still have a higher rate through each subregion. So we did better than this, but it's still underestimate. Is this making sense?
Yeah, so basically what it is it's similar to how we did in Calculus 1, where we're partitioning the region into...
Right. Yeah, now the thing we're partitioning is 2 dimensions. Before you partitioned just along the x-axis. You partitioned the x-axis. Now you're partitioning in 2 dimensions. All right, so keeping hold of that, what we just did, now I want an even better estimate. What would I do?
You would either do midpoint or partition it.
Yeah, finer partition, right? So better estimate. You get from finer partition, meaning more subregions. The more subregions you use, and then say use your lower left still, you're going to get better and better estimates. Okay? So this is, someone said this is like a Riemann sum, right? And so it's true, but now we have two variables. We have two variables, so it's a double Riemann sum. And what are we summing up? We're summing up the rate and so different rates, so we can like have an I, and J. So according to the partition, we could like I would be maybe the horizontal and J would be the vertical location according to our partition. So then, and we're summing up that times our dt dE. Right? So we take each little amount of the quantity and we're going to sum all those up. But it's a double sum because there's two variables. And so how do we get, so again, the finer the partition, the better the estimate, but we want to get something close to exact. We want to get something close enough to where we say, okay, this is the actual megapounds of snow that fell there. What would that require? Our partition is so fine that dt dE is like a point square. Super small point squares and a gazillion of them, right? A gazillion of them. So that in each point square, we just are really just pulling off the value of the function. They're so small that you don't use lower left, upper right anymore. You just take the value of the function at that quote unquote point. And so when we do that, what do we get? This becomes, so let the number of subregions get really big. And when we do that, this Riemann sum turns into what? You guys remember? Yeah.
Is this a surface integral?
No, not quite a surface integral yet, but a double integral. So it's going to be a double integral. Okay? A double integral. And now instead of picking off individual points of rate, it's like all the rates. Because the little squares are so small, it's like a continuously pulling off all the rates times the little changes in dt and dE. And so then this inside integral goes with this variable, right? So the first variable here matches up with this. So t is going from 1.4 to 1.8. Can you still see that 1.4, or am I too close to the bottom? Can you see that I wrote 1.4 there?
Yes.
And then E, so then so it's kind of like inside out. So the t, the first variable here, matches up with the inside integral here, and then the outside to the left, dE, will match up with this, and it's from 5 to 6, right? So here now we have the exact weight of snow as t changed from 1.4 to 1.8 and E changed from 5 to 6.
So it's similar kind of to what we did with the partial derivatives. You're just taking it with respect to each variable. This is similar, but it's just going backwards, right?
No, it's not going backwards. We did lots of calculations where it was the partial derivative times the change in x, or the partial derivative times the change in y. So that was the same. Like we were finding little changes in our dependent variable, right? But now the difference is now we are adding them all up to get like an accumulated change. So we didn't do that before. So now we're adding up all those individual changes across your dt and your dE to get the total accumulated change. In this case, the weight of snow from 1.4 to 1.8, or the elevation range from 5 to 6,000 feet.
Thank you.
So is there a name for this multivariable rate? Like, is it a type of derivative that like a partial derivative, there's like a way to calculate that.
No, in fact, I kind of made up that name myself, so I don't know what the rest of the world calls it, but it's a rate of change function, but with respect to two variables, so I'm calling it a multivariable rate function. So a real common example of that is like a density function, right? It's like how much stuff you have per unit area. So that's another good example of a multivariable rate function. Like if
so it varies like with the change in every dimension.
yeah, just like this, like the contour plot is a continually changing value, right? So as soon as you have a different time, your rate changes. As soon as you have a different elevation, your rate's continually changing. And that's why to get this amount of snow here, we've got to make our partition super small, right? To actually get the amount of snow that's fallen in these two ranges. So that we're taking into account like every rate in there for every point square.
Thank you.
Okay, you're welcome. So we gotta advance the conversation here. All right, so then, is there a question?
Yeah, for the quiz, it's locked. It's still.
Yeah, I know. I got one more thing to tell you so you can get the last one right in the quiz. So let's do that. Sorry about that. All right, so now we're going to look at that same multivariable rate function. And that's what we did. That's how we just did with the double integral. So now the same multivariable rate function is shown here, represented as the surface. So this contour plot is equivalent to this surface. And so we have our t here, t-axis. And so, for instance, we could go here from 1.4 to 1.8. Same change in time. And then here's this axis, the e-axis. And so we could go from say 5 to 6. And so that would make our square here in the x or the TE plane. 5, 6, like this. And so we're talking about lower left corner. So everything's turned now. Where's the lower left corner of this whole region? Where's the lower left corner of the whole region?
Leftmost corner of the diagonal.
Be here, right? This is lower left. So it's like you're standing here looking this way, right? Lower left. So the lower left, upper right is always in reference to the XY plane, the way that we orient it with, X to the right and Y up. So you're standing here, you're looking, there's lower left. So same thing, we broke it up like this. So there's lower left, lower left, lower left, lower left. Okay, so for this one out here, I think it was this right here. So I think this is where we were, right? Yeah. So this sub-region right there is this one. Am I right? And so let's take a look at something. This length right here is DE. This length right here is DT. And then we did the lower left. And so how does the rate show up in this graph? How do we see the rate in this graph? So we picked that corner. So where's the rate shown geometrically? Height, right? To the surface. So really what we did was we took dt times dE times this height. So what did we find when we were finding that little change in snow? Weight. Do you see what else we found? So when we did dW equals the rate times dt times dE, that was a little bit of snow weight. But now we have a different way to interpret that. What is that? Is it the volume of this rectangular column? Beneath the... So the volume of this rectangular column is the same thing, length times width times height. So then what would the integral of f dt dE give?
The volume.
So now you got a billion little subregions, each little square times the height up to the surface. So what does that give? The volume of?
Underneath that square.
Right. It's the volume between F and the horizontal plane and the TE plane, or the like XY plane. So see if I can draw that real quick. So it would look like this. And whereas it's lowest here, and it kind of goes up this way and up this way. And highest here. Let's see how I did. Oh, that's pretty good. All right, so it's like the highest here, lowest back there in the lower left. And so the volume of this thing beneath the surface down to the horizontal plane, constrained by our square, that's the geometric interpretation of this value. So the rate of change version that's the accumulation of the weight of snow for those two ranges. Then when you take your rate function and make it a surface, you're actually finding you're finding the volume below that surface down to the XY plane.